stabilized lander.
Good afternoon. I'm NASA Shaniqua Vereen, and we are live inside the White Flight Control Room at the Johnson Space Center here in Houston, Texas. We are bringing you live coverage today of the distant retrograde orbit departure burn. This is a quick burn expected to fire for 1 minute and 45 seconds, beginning at 3:53 and 50 seconds p.m. Central Time, 4:53 p.m., 45 seconds Eastern Time. The distant retrograde orbit is an elliptical orbit or oval shape around the moon. This orbit is unique to Artemis I, testing out its various systems, and will not be used on future Artemis missions. Later, we'll have NASA's Dan Hewitt back at the moon board to explain a little bit more about the distant retrograde burn and how it affects leaving the distant retrograde orbit. And NASA's Robin Elgart is here later today to talk to us about the deep space radiation environment and what she is doing to help further our knowledge on space beyond lower Earth orbit. We'll catch up with them a little bit later, but for now, here are some shots inside the Artemis Mission Control Room. And we're hoping for some views from Orion a little bit later. Currently, you're seeing the arrow tracker used to track Orion. Seeing current velocity, distance from Earth, and distance from the moon. Following a successful launch on Wednesday, November 16th, NASA's uncrewed Orion spacecraft is ready for its distant retrograde orbit departure burn today on day 16 of its 25-and-a-half-day mission beyond the lunar surface. Orion lifted off atop the Space Launch System rocket at 1:47 a.m. Eastern Time from Launch Complex 39B at NASA's Kennedy Space Center in Florida. The distant retrograde departure burn prepares Orion for a second lunar flyby, or that RPF, the return powered flyby, and Earth insertion burn, and finally preparation for a re-entry and splashdown planned for December 11th. So as we recap some of the milestones thus far for Orion, on November 21st, Orion performed an outbound powered flyby burn, the first of two maneuvers required to enter DRO, or the distant retrograde orbit, the second being the insertion burn that happened later that week on November 25th. At the time of the outbound powered flyby, Orion was just 81 miles above the lunar surface. Throughout the mission, the spacecraft performed a series of outbound trajectory correction burns to put Orion in the proper configuration to enter the distant retrograde orbit. So remember, 81 miles above the lunar surface on November 21st, and by November 22nd, Orion exited the gravitational sphere of influence of the moon and was at a lunar altitude of nearly 40,000 miles. Orion surpassed the distance record for a mission with a spacecraft designed to carry humans to deep space and back to Earth at 7:42 a.m. Saturday, November 26. That record was set during the Apollo 13 mission at 248,065 655 miles from our home planet. On November 28th, flight day 13 for Orion, Orion surpassed, it reached its maximum distance from Earth during the Artemis I mission, and it was at 268,563 miles away from the home planet. And finally, on November 30th, just yesterday, teams polled go for Orion to exit the distant retrograde orbit. Today, we are live covering the distant retrograde orbit departure burn, or the DRD, which will bring Orion out of the distant retrograde orbit to prepare Orion for a splashdown back on Earth. Again, splashdown is planned for December 11th. And we are looking for the burn for the distant retrograde orbit departure burn to happen at 3:53 and 56 seconds p.m. Central Time. Again, let's get a little insight from NASA's Dan Hewitt at the moon board.
It's been a fantastic mission, but all great things must come to an end. It is time for Orion to leave its orbit around the moon and come home. So we are getting ready for distant retrograde departure. This is going to be a firing of those engines on the European service module to actually commit us to leaving the lunar orbit and coming back towards Earth. So we're again going to be using that large main engine to start to swing us back in close so we can do essentially a slingshot around the moon. We'll be dipping in again for another powered flyby, this one called the return powered flyby, which is really going to kind of fine-tune our path back towards the atmosphere. But the one really committing us to come home is going to be this one that's coming up, this distant retrograde orbit departure. So for Orion, it's going to be farewell to the moon until it starts making its way to us back here on planet Earth.
Back inside the Artemis Mission Control Room, or the White Flight Control Room here at Johnson Space Center, we see the control room, and we have lead flight director for Artemis I mission, Rick LeBrode, and his team monitoring and preparing for this upcoming distant retrograde orbit departure burn. Here with me now, I have a special guest today on console. This is Robin Elgart, space radiation element scientist. She will discuss the deep space radiation environment and what we are learning on missions like Artemis I. Hi, Robin. Thank you for joining me today.
Thanks so much, Shaniqua. I'm happy to be here.
And can you tell everyone what a space radiation element scientist is?
Of course. So as a space radiation element scientist for the Human Research Program at NASA, I am responsible, along with my excellent team, for developing and executing a robust research strategy to understand, characterize, and hopefully mitigate the health impacts to humans from the space radiation environment. And so when we talk about space radiation, why does NASA care? Well, turns out space is a radiation environment, and so our astronauts are actually radiation workers. And so that means that we know that radiation is a health hazard for them, and we need to do our best to characterize that and mitigate that. And so this radiation comes from 3 different places in our universe. First, we have our galactic cosmic rays. Galactic cosmic rays are theorized to be the result of stellar explosions, where things like supernova are accelerating particles throughout the universe. Right? And so you can imagine how fast these particles are going. And then we have trapped radiation. Trapped radiation is actually a consequence of our Earth having a beautiful magnetic field, and it protects us from all sorts of things, but it also traps some of that radiation that's zipping around out in our solar system inside these belts, which are called the Van Allen belts. So those are these sort of donut-shaped rings around our planet. And then thirdly, and probably the most well-known, are solar particle events. And these are when the sun sort of belches out some extra solar particles and out into our solar system.
Okay, and you mentioned solar particles. Can you explain a little bit of what those are and how they could affect the Artemis missions to come?
Absolutely. So the sun is a giant rotating ball of magnetized plasma, which is sort of mind-blowing when you think about it. And it creates an incredibly complex magnetic field throughout our solar system and also on the what we think of as the surface of the sun. And those some localized areas of the sun those magnetic fields in those localized areas can get really tangled up and entangled with each other. And that creates something that we all know of called sunspots. And you can actually see these with the appropriate kind of telescope from down here on Earth. These sunspots can create sort of active regions where the local magnetic fields are really entangled. And just like anything, you can, something that builds and builds and builds energy, at one point it just gives up. And so these magnetic fields, they break and they reconnect down into a lower energy state. That energy has to go somewhere. And so that energy is released at this huge amount of energy release, some of which can actually push particles out from the solar corona, as well as the particles out in the solar system out into the solar system. And so that's what's called a solar particle event, when those particles are accelerated out from the sun out into the solar system.
Awesome, and that is definitely something worth caring for. On Artemis I, on flight day 13, on November 28th, Orion reached its maximum distance from Earth. Now, we know that that maximum distance was 268,563 miles from our home planet. How will being further from Earth affect our crew on future Artemis missions?
That's a great question. So because those Van Allen belts that surround Earth and protect us from things, beyond those, the crew will no longer have protection from galactic cosmic rays, those particles that are accelerated because of supernova, or those solar particle events. So if there's a solar particle event headed your direction and you're outside the Van Allen belts, you have no protection from our beautiful, snuggly Van Allen belts anymore, right? And so them being further away from Earth means that in mission, real-time monitoring of the solar environment is really important, because if you are going to be exposed to these solar events, we have to have some way to shield it, because even though we can't shield from galactic cosmic rays, we can shield from solar particle events relatively effectively, and it doesn't take much. So our operational team, the Space Radiation Analysis Group, or SRAG, they've actually developed an awesome protocol, which is to build a storm shelter. And I think we have a great video that demonstrates what this looks like.
My name is Jessica Voss, and this is Ann McLean, and we are here today helping the designers of the Orion capsule evaluate the ability to protect their crew from radiation. Radiation, as you know, is really harmful, and so the whole point is for us to get into a really cool little shelter and take all the equipment we have in this capsule and put it over us as best as possible. And we have to make sure it's stowed and that we are safe and we have everything we need in terms of supplies down in this awesome little bay.
So you can see there, they build this basically is what amounts to a pillow fort, and putting all of that mass around them to keep those lower energy particles from solar particle events out of their little pillow fort there, and keep them sheltered from that storm.
And you're saying pillow fort, but the pillow fort is stowage bags and different things that are already in Orion for the crew, and they're using that during a solar particle event to protect themselves.
That's exactly right. And so they can hang out in that little area for the entirety of the event. Of course, they can come in and out of that shelter. They don't need to stand there the whole time, but we want them to spend as much time as they feasibly can inside that shelter. And right, it's just using stuff that we already have on board to sort of even out that mass distribution.
Gotcha. And so as far as protection goes, again, for our astronauts on future missions, we know this is an uncrewed mission, but future missions will have astronauts aboard. What can we expect beyond this for astronaut protection in terms of radiation?
Great question. So like you said, this is, it's uncrewed, but even on these first short-term missions, we are still learning things about the radiation environment. We have a radiation detector up there now, HERA, which is constantly taking data right now, and we're actually seeing how those what makes that pillow for it. We have a sensor in there right now, and we can see that it actually is providing protection compared to the sensor that is outside of that bay when they transited through the Van Allen belts, because it's a similar type of radiation to solar particle events. But moving forward, the uniqueness of the space radiation environment really makes for a hefty challenge when it comes to doing research down here on the ground. So we don't have the same amount of protection strategies up in space as we do down here on the ground. Usually when you're in a radiation oncology department, you have time, distance, and shielding. Well, in space, you can't get away from the solar radiation and the galactic cosmic rays, and you can't really shield it either. So the only thing we have is time. But of course, if we're talking about a year mission to the moon, we're talking about 3 years mission to Mars, time starts to become a problem too. So that's where the space radiation element is coming up with new strategies of how we might be able to protect the crew, which includes things like health monitoring, early disease screening for the things that we are concerned about, including cancer, cardiovascular disease, immune changes, and potentially even neurocognitive defects, as well as looking for some sort of compound-based countermeasure that can help the body protect itself from that biological damage. We might not be able to stop the physics, but we might be able to help the biology.
That's amazing. I know our crew will need to be protected from those rays as we enter into future Artemis missions. On our future missions, we talked about the protection, we talked about space radiation. Is there anything left that we didn't talk about that would be relevant to what we're learning about space radiation on this mission or even future missions that are planned?
On this mission in particular, I really just want to give a huge shout out to our operational team, the Space Radiation Analysis Group, because they have worked so hard on getting their detectors up to speed, and they're really starting to see their models play out. You know, they saw when Orion went behind the moon and came back out, and we finally got that signal again. Sure enough, there was a 30% drop because of the moon itself providing shielding to the capsule. And so just a really huge shout out to that team, because they have done an amazing work. They're working 24-hour console to support this mission, and they really deserve mad props.
Thank you very much, and thank you, Robin, for coming and joining us here today, telling us a little bit about the deep space radiation environment and why it's important to the Artemis missions overall.
Thank you so much, Shaniqua. Happy to be here.
Thank you. And if you just joined us, you're watching live coverage of the Artemis I mission. Today, we're on day 16 of the 25-and-a-half-day mission. We are currently awaiting the DRD, or the distant retrograde departure burn. And we're looking for that burn to happen at 3:53 and 56 seconds p.m. Central Time, 4:53 and 56 seconds p.m. Eastern Time. So about 4.5 minutes out now from that burn. If you're just joining us, we're live inside the White Flight Control Room at the Johnson Space Center. We are awaiting the departure burn. That's the distant retrograde orbit departure burn for Orion. You're currently seeing live views from Orion spacecraft as it prepares for just a minute and a half from now to do that burn. And just about 10 seconds away from that burn beginning. The burn has begun. And we're halfway through the burn. And we currently see a little Earth beside one of the Orion solar arrays coming into view and out of view as this burn continues. And a nominal burn has been called in the room. And with a nominal distant retrograde orbit departure burn, Orion will leave its distant retrograde orbit, preparing Orion for a second lunar flyby, that return-powered flyby burn that we discussed earlier, an Earth insertion burn, and finally preparation for re-entry and splashdown planned for December 11th. Again, Orion has had a nominal 1 minute and 45-second distant retrograde orbit departure burn. And with that, we'll wrap coverage for today. But we'll be covering the RPF, or the return power flyby burn, live on air on Monday, December 5th. Again, that will be aired at 8:30 a.m. Central Time, 9:30 a.m. Eastern Time. And again, that is on December the 5th. Before we air that December 5th return power flyby for Orion, be sure to check out live coverage of the U.S. EVA on December the 3rd. Showtime beginning at 5 a.m. Central Time, 6 a.m. Eastern Time. Our live views from Orion have gone. Briefly, we are currently looking at the Aero Tracker. You can track Artemis and you can track Orion on www.nasa.gov/track-Artemis. Again, this is the Aero Tracker, giving you the velocity, the distance from Earth, and the distance from the Moon for Orion in real time. Again, we had a nominal distant retrograde orbit departure burn. Orion will leave its distant retrograde orbit, preparing Orion for a second lunar flyby, an Earth insertion burn, and finally preparation for re-entry and splashdown planned for December 11th. That'll end our coverage there. However, we'll be covering the RPF burn live on air on Monday, December 5th, beginning at 8 a.m. Central Time, 9 a.m. Eastern Time. And before that burn coverage, we also have live on air Saturday, December 3rd, the U.S. Spacewalk 82, and that will start at 5 a.m. Central Time, 6 a.m. Eastern Time. And be sure to follow along with our daily blog posts as Orion continues its journey to the Moon and beyond and prepares for its trip back home. Follow the blogs at blogs.nasa.gov/Artemis. Again, thank you for joining us, and that'll wrap coverage for today. This is Mission Control, Houston.